Welcome to this presentation on drilling-induced fractures in drill cores, a review paper authored by Shatavisa Chatterjee and Professor Soumyajit Mukherjee from the Department of Earth Sciences, IIT Bombay. This paper provides a comprehensive overview of the types, mechanisms, and geomechanical significance of drilling-induced fractures, or DIFs. Today, I will walk you through key theoretical insights and figures from the paper, with a focus on how DIFs are applied in both academic and industry settings. You can scan the QR code provided to directly access the original research paper. Drilling-induced fractures form as a result of stress concentration around the borehole. When the local tensile stress exceeds the tensile strength of the rock, failure occurs. This is especially relevant in high-stress environments, where anisotropic stress fields are prevalent. DIFs provide us with real-time indicators of the in-situ stress field. Importantly, DIFs occur in the compressive stress regime, where redistribution during drilling causes tensile failure in the rock matrix. DIFs are tensile fractures generated during drilling due to concentrated stress redistribution. They appear in drill cores and wellbore walls and are typically aligned with the maximum horizontal stress direction, SH. In vertical wells, they are oriented perpendicular to wellbore breakouts. The occurrence of these fractures provides crucial insight into wellbore mechanics, rock stress anisotropy, and failure processes. Figure 1 in the paper introduces us to the different morphologies associated with DIFs, including disc, pedal, pedal centerline, and saddle types. The role of DIFs in subsurface characterization is multifaceted. They allow us to determine both stress orientation and its relative magnitude. For example, by identifying fracture types and their orientations, we can distinguish between extensional and compressive stress regimes. Moreover, DIF analysis can predict problematic drilling zones, prevent wellbore collapse, and optimize mud weight design. In mature reservoirs, DIFs are also used to model fracture networks and analyze reservoir connectivity. DIFs are classified based on their geometry and initiation mechanics. The key morphologies include disc, pedal, pedal centerline, saddle, and scallop types. Figure 2 provides both photographic examples. Each type reflects specific stress conditions. Disc fractures are commonly formed in isotropic stress fields, while pedal and saddle fractures develop in highly anisotropic settings. Understanding the morphology helps in correlating core observations with downhole stress conditions. Disc or cup-shaped fractures form due to vertical tension in fine-grained rocks, despite originating under compressive stress. These appear as subhorizontal features in vertical cores and often split the core into puck-like segments. Figure 3. The plume axis in these fractures aligns with SH, as shown in figures 3 and 4. Pedal fractures result from a high SH to S(h) ratio. They appear as curved fractures originating from the base or edge of the bit and curving inward. As depth increases or horizontal stress anisotropy reduces, these pedal fractures evolve into pedal centerline and disc fractures. Figures 5 and 6 display examples of these features. These fractures provide crucial insights into temporal stress evolution during drilling and are especially useful for directional drilling analysis. Transverse fractures, including disc, pedal, and saddle types, form perpendicular to the core axis and are critical in stress modeling. Figure 7 shows how they appear in image logs. By analyzing the shapes and spacing of these fractures, we can constrain the SH and S(h) values and infer the tectonic regime. For instance, curved pedals are indicative of high SH/h anisotropy, while symmetrical disc fractures reflect isotropic conditions. These features help classify the stress regime as normal, strike slip, or thrust faulting. Figures 8, 9, and 10 demonstrate DIF formation under different tectonic stress regimes. In normal faulting, SV greater than SH greater than S(h), pedal fractures dominate, indicating extensional environments. In strike-slip regimes, SH greater than SV greater than SE(h), mixed fracture types form, depending on stress anisotropy. In thrust faulting, SH greater than SE(h) greater than SV, disc and saddle fractures are prevalent due to higher compressive stress. These figures visualize the progression of DIFs with changing stress ratios and help interpret the regional tectonic setting based on core samples. The fracture intensity and distribution depend heavily on the core stub length. Shorter stubs experience concentrated tensile and shear stresses. As shown in Figure 11, the maximum tensile stress is achieved when the stub length is approximately 25 to 40% of the core diameter. Understanding this relationship helps design better core acquisition strategies and assess the extent of induced damage. Core length is thus a key factor in interpreting true in situ fracture behavior. In non-vertical wells, the principal stress axes reorient relative to the borehole, complicating fracture interpretation. This often leads to the development of en-echelon DIFs, where fracture sets appear as staggered patterns. Figure 4, supported by experimental studies like those by Jia et al., 2015, shows these en-echelon features. This understanding is critical for analyzing wellbore stability and fracture propagation in deviated and horizontal wells. Image logs, such as those from Formation Microimager, FMI, or Borehole Televiewer, BHTV, are essential for visualizing DIFs in situ. These fractures appear as dark, conductive features due to the mud infiltration. Figures 12 to 14 provide examples of pedal and disc fractures in vertical wells. Pedal fractures show up as symmetric features separated by 180 degrees. Such logs not only confirm core observations, but also allow continuous downhole analysis of stress orientation. One challenge in fracture interpretation is distinguishing DIFs from natural fractures. Figure 15 outlines various criteria. DIFs are typically smooth, lack mineral fillings, and align with SH. In contrast, natural fractures may be offset, irregular, or filled with minerals. The presence of triangular fracture sets or radiating cracks near the core edge also hints at DIFs. Accurate differentiation is crucial for proper geomechanical modeling and reservoir characterization. DIFs are essential tools in subsurface geomechanics. They are used to constrain the orientation and magnitude of horizontal stresses, SH and S(h), which are critical for wellbore stability, hydraulic fracturing design, and reservoir management. Studies across various basins have utilized DIFs for practical insights. In the North Sea, DIFs helped evaluate hydraulic fracture reactivation and well completion strategies. At Shah Deniz Field, image log analysis of DIFs informed sidetrack drilling and geomechanical modeling. In Antarctica, DIFs were used to infer present-day tectonic stress fields despite minimal seismicity. In Western India, DIF studies revealed the presence of transpressional stress, aiding regional tectonic interpretation. These applications span hydrocarbon exploration, CO2 sequestration, and geothermal development. The table in the slide summarizes case studies, tools used, like FMI, acoustic logs, CT imaging, stress regimes, and interpreted DIF types across 18 regions worldwide. Figure 16 and Table 1 summarize global DIF studies. These include regions from Antarctica to India, where DIFs have been used to build geomechanical models and understand stress-induced hazards. Some studies used DIFs to back-calculate pore pressures, while others correlated DIF orientations with fault trends. The diversity of applications highlights their value across both academic and industrial settings. Future research should focus on improved DIF detection in inclined and horizontal cores. The integration of 3D visualization tools and AI/ML models can enhance DIF identification and classification. Modeling fracture propagation using real-time logging data and lab experiments on analog materials will also help. Advanced imaging tools and digital rock physics can push the frontier of DIF analysis beyond current capabilities. DIFs are a powerful tool for interpreting in situ stresses. Their morphology, orientation, and frequency help inform reservoir engineering and wellbore design. Recognizing different DIF types aids in identifying drilling risks and optimizing production. The integration of core studies with logging data is essential for building robust geomechanical models. This presentation is based on the review article authored by Shatavisa Chatterjee and Professor Soumyajit Mukherjee of IIT Bombay. I would like to thank them for their detailed and insightful contribution to the understanding of drilling-induced fractures in drill cores. If you have any questions or would like to discuss this further, please feel free to reach out to the email address shown on the slide. You can scan the QR code provided to directly access the original research paper. Thank you for your time and attention.